2, lesson 2.2, so the power rule. So it'd be time consuming and tedious if we always had to complete derivatives directly from the from the definition of derivative, that's what that is. Okay, using the limits a plus h. Okay, fortunately there are several rules that can greatly simplify differentiation. Okay, we're going to learn these rules, so we'll kind of briefly go over them, but we're only doing product rule today. There's product rule, there's sum and difference rule, there's quotient rule, and there's chain rule. And I think there's one more, but anyway, it's kind of a rough idea. And they're rules based off of operations. Okay, derivatives kind of come from operations. But the first rule tells us how to find a derivative of a constant function. So just reading this, what do you translate as? F of x is a constant, therefore f prime is 0. The reason is the derivative of a constant is 0. Does anyone want to take a guess of why that is? Just thinking based off maybe what we talked about yesterday. So if you're here yesterday, you might have an idea. But why would the definition of the derivative of a constant be 0? There's no variable. Good. There's no slope. Good. Because a constant, f of x equals 2, what kind of line is that? A horizontal flat line. Okay? So then the derivative of that would be 0. Okay? We're going to get to that some more a little bit later, but basically your first rule that you're going to write down is kind of a simple one. When taking the derivative of the constant, essentially it goes away. It's 0. Okay? Okay? So, just want to see if I'm going to do the proof here real quick. Yeah. So we still writing that? We're good? Okay, so we're just going to kind of go through the proof of it real quick. So if you were to prove this, you take the limit of h goes to 0 of x plus h, blah, 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 but we're going to call them constants now. So there is no x's. So if that was the case, you know how we plug in x plus h in for x? We wouldn't do that now because they're just constants. So if you did that, you get c minus c over h, which is 0. Okay, and so that's how come the constants wouldn't cancel. So what I'm saying is, you understand, let's go over here and look at our warm-up. This part wouldn't happen because there's no x's. So we wouldn't even have to plug x plus h in anywhere. So that's how come it becomes 0. Well, 0 over 0 because... Right. Right. Yeah. Okay. And again, it comes from the idea, what you guys said earlier, it comes from the idea that it's a flat line. So figure illustrates a constant rule geometrically. The graph of a constant function's f of x is c, is the horizontal line y equals c. The tangent line at any point in this line is the line itself. Okay. Since the horizontal line has a slope of 0, the slope of the tangent line is also 0. Okay. Very good. Yep. And we're going to get to an example here. Okay, for those of you who were here yesterday, just a brief review. A couple things as you guys are asking in the warm-up. Yeah, this stands for derivative. This stands for derivative. Okay, that sounds a derivative of y with respect to x. Okay, that's what this essentially, these two mean the same thing in terms of notation. Stands for derivative. Okay. All right. Okay, so example 1. If f of x equals 7, then f prime of x equals 0. Okay. If y equals pi, then y prime equals 0. And the derivative with respect to x of negative 4.5 is also 0. So all three of these are examples of constants that are equal to 0. Reason we recognize, okay, well, 7 is a constant. We know that. Pi is still a constant. It's a number. Okay, it's not a variable. I know some of us think pi is actually an x or something. It's not. It is a number, so derivative of pi would be 0. And derivative with respect to x with something without an x would be 0. So derivative with respect to x, that's what d over dx means, of negative 4.5 is also 0. So we're kind of walking down into the power rule here, and then we'll kind of do some examples and pretty much be done. A little bit more definition to go. Okay, so the next rule gives a formula for differentiating the power function, f of x equals x to the n. We have already computed derivatives of special cases of the power function. Example 3 of 2.1, we showed that the derivative with respect to x of x squared was 2x. We did that. Remember, we talked about how if we wanted to find the slope of a given point, we would plug it in there for x. So if we want to find that x equals 4, it'd be 4 times 2, we'd get 8. So it is a function. Okay, the derivative of that x squared was a function that changed. And I showed you guys that picture, etc. Do you guys remember talking about? So just a quick refresh. So we have like a parabola, for example, because x squared is a parabola. Okay, and if I'm going through this, that will say it's like a slope of 2. And it hits like right there. If I want to go through right here, what's going to have my slope? It's going to get what? Steeper. So that would be like 8 maybe. Okay, well then if I want to go on this side, I would now have negative slope, like -2. And then up here would be like -8. Okay? And that comes because, what would I plug in? Over here, I mean, this is x squared, so it's right down the middle. So like this is like 2 and 4. If I put 2 in, I'd get 4. If I put 4 in, I'd get 8 for my slope. If I put -2, I'd get -4. If I put -4, I'd get -8. So it's just the idea that the slope changes around the parabola. Okay, just using your positive, negative numbers. But at any rate, if you can just understand that the derivative of the function gives you the equation, okay, because we have to know, like from our warm-up, we need to know an x to evaluate if we want to be specific. Okay, otherwise, we can get a equation that will represent our derivative. Okay, so with that said, this is what we're doing today. If I was doing x cubed, you can see the pattern. The derivative of x cubed is 3x squared. So what are they doing in terms of maybe a rule that you're seeing? What do you see? Or how about x to the 4th? Right, the power becomes the coefficient, and you drop the power 1. So drop the 3 down, now it's a 2. Drop the 4 down, now it's a 3. Okay, that's essentially your power rule. Okay, and you can kind of see it from over here. Just, I know it's not on the notes here, but from the warm-up, what would the derivative of this one be? What's x squared? 2x, right? Drop the 2 and it'd be x. And then what's the derivative of 7x, you think? So a single variable. What? It'd just be 7. Because you drop the 1, and now what would the next one be? X to the 0. What's x to the 0? Just 1, so the variable goes away. Does that make sense? So 2x plus 7. Now I want you to do really quickly is plug in 3 to that. What's 2 times 3? Plus 7. 13. That's what we're doing. Okay? It's making your life a lot easier. Okay? Let's keep going here. So then here is your definition of the power rule. So I can't talk today. To differentiate, okay, drop your n, drop your exponent, and then change your exponent to n minus 1, essentially subtracting 1 from your power. Or exponent power is not the proper math definition there.
I think that would just be 7 because you go x to 0. So it disappears.
For the 7x?
Yeah.
Yes, exactly. So if you have I'll state what you're talking about. If I have 7x, that's to a 1. So 1 would drop down. 1 times 7 is still 7. Now be x to the 0. Remember, x to the 0 equals 1. So it's just 7. That's how it would go for a single variable. Any questions on that? So this is the main, hopefully if you're taking notes, this is the main thing you want to write down today. This is the power rule. think I might. All right, so just a general skim through of the proof, and this is in your book if you'd ever care to look at it. But essentially what you would do is understand that the patterns are growing by one exponent. So when you plug them in, and we do like this is essentially we're doing a series. Okay, that's why you see those pluses. You're pretty much going to be adding, everything's going to cancel except for the previous one. And so what you're left with is simply the previous term all the time. So that's why we do the n minus 1. So just without going through that being super complicated, just think about when you're evaluating these, the x minus a's will cancel, and you're looking at the previous term every time. So that's where the power rule comes from, the previous term. So let's get to some examples here. Okay, so they're already these are quick examples. They're kind of already on here, which isn't as fun. But so x to the 7, the derivative of x to the 7 is 7x to the 6th. So you drop the 7, now it's a 6. X to the 100 would now be 100x to the 99. Pay attention to the notations here. So you can write derivative as f prime of x, y prime, derivative of y with respect to t. So with respect to t, that means that's what you're differentiating. Okay, y is what the equation is in. So that would be 5t to the 4th. And then lastly, derivative with respect to u of u9 would be 9u to the 8. Okay, and then this next example here, after you guys get done writing, this next example is going to be the one that you're going to be like, it's making you mad about yesterday. All right, so just to refresh here, constants are irrelevant on the derivative because a constant of derivative of a constant is 0. All right, so example 3. So now we're going to kind of put together. It says find the equation of the tangent line of the curve y equals x to the 6th at the point -2, 64. So when we see equation of the tangent line, we immediately think derivative now. Okay, this is one we can do the power rule. So we have y equals x to the 6th. We want y prime, okay, which is going to be 6x to the 5th. And now I want to evaluate that at -2. So we put -2 in. Okay, so we're going to do 6 -2 to the 5th. Okay, that's going to give you, when I calculated that, I got -192. So what is this? -192 is what? Because we're finding the equation. It's the what? It's the slope. Good, so -192 is my m. So what I want to do is, I need to solve. Remember, we need to use both these points now. Okay, so I'm going to go 64 equals -192 times -2 plus b. And we're just trying to solve for b now to finish my equation. Okay, so I got the -192 from calculating this right here. That's where this came from. I got the 64 for my y up here, the -2 for my x up here. Okay, so that gives me 64 equals 384. And it's positive. Minus 384. That gives me -320 equals b. So our equation is that right there. Exactly. We're using rules, like I said in the very beginning, we're using rules to get around that tedious time. And so I'm going to teach you one rule at a time to help you with each situation. So, oh, sorry. Sure. All right, so Although we have proved the power rule when its exponent is n as a positive integer, it turns out it's true for any real number. And guys, this is very important for you to really understand your exponent rules. What I mean by that is, if something's on the bottom of a fraction, like an x, what if you have 1 over x cubed? What could we call that? Yeah, if I had 1 over x cubed, it's important if you could see that as x to the negative 3. It's easier to take the derivative that way. Okay? So being really good with your exponent flips and stuff like that is going to be helpful. Okay, your exit card today is one of those. So just keep that in mind. Okay, another thing just keep track of. What is this as an exponent? 1/2. Good. So then if I put it on the bottom, it'd be, right, just these type of things you need to be good with your exponents. If you're not, you need to get to me quickly so we can get you caught up. Okay? That's what this rule is telling you, is that we can do it for any number. Okay, so if we did do it, let's say if we did do it, let's just do x to the negative 3. What would the derivative of that be? No. Negative 3x. I'm not going to do any fractions. We'll leave it in negatives. Negative 4. You're minusing, right? Very common mistake. Now, if you want to write this, now you could write over. You could do it like that if you wanted now. Okay, and that's fine. But the big problem there, I made sure I want somebody to say negative 2. Everybody does that. You got to drop 1. If you're dropping 1, you're going further negative, right? Okay, common mistake. Walked right into it. All right. Oh, I really think it's really, really weird when I'm doing random examples like I didn't know, and then it's the next one. It's like I think that must be something like there's got to be some science on that, because I do that all the time in my math classes. I'll do an example. I think I made it up, but it's coming. All right. So like we just did this one. Okay, so write as x negative 3. Then it'd be negative 3x to the negative 4. Okay, and a lot of times they do, though, like I just told Darby, they do want it in positive exponents, so you can push it down.
You don't have to.
Yeah, unless they tell you to. Sometimes it's easier for what you're doing, but you don't have to. I think in general I probably would. Most of the time it's going to make your life easier. Okay, and then the B, so y equals root x, which we just talked about as well, which is x to the 1/2. So if we were to do this one, this is where things get a little tricky. You got to be good with your fraction stuff. What would just the derivative of x to the 1/2 be? Negative 1/2, which would be, if we wrote it in positives, it'd be 1 over 2 root x. Because the x to 1/2 will move down. The 2's already there. So this is just root x, but on the bottom. Okay, getting tongue-tied over there, Austin. Questions? Anything on that? Okay, not too bad. Hopefully. Yeah, you can leave it. Yeah, this part's not super crucial. Okay.
Why would it be 1/2? Like move the power to the coefficient, and then you subtract 1 from the original power to get the new power.
Right, because 1/2 minus 1's negative 1/2. So it just kind of bounces over. And that's just because it's a fraction. So like if I did 3/2, and I dropped 3/2, I minus 1, I'd still be in the positives, right? So I'd still be up. So it just happens with this one, since it's smaller than 1, and I'm subtracting 1, I get negative. Okay. This is a common, and I would say, maybe your notes, maybe just kind of star that, remember that. That's a very common mistake I see throughout the years. People forget to make it negative. Okay, they forget to minus the 1 to it. So just keep that in mind. Okay, let's look at a couple more here. All right, so first off, so the next rule says that the derivative of a constant times a function is the constant times the derivative of the function. So, okay, so if you have g of x equals a constant times f of x, then g prime of x equals a constant times f prime of x. Okay, and we'll kind of get to why this is important if you want to write that. And then here's kind of the proof of it, but again, I'm not going to, I feel like I don't need to bore you with that. Just it's there if you'd like to see it. On here. So example here is to differentiate f of x equals 8x cubed. So all this is saying, okay, I know it was confusing, it's just telling us we can take a derivative if there's a constant in front. All you do is you multiply by it. That's all that rule was. We dropped the 3, we times it to the 8. That's all that rule was. Yeah. That's why I didn't want to just over-explain it to you. You just drop the 3 times to the 8. Why do we have to make it look Japanese? So it's 24x squared for A. Exactly. Drop to 2. Drop the 1, yeah. Okay, but let's look at this one, which is a little more confusing in terms of your fraction skills. So you're still going to drop 8/3. So you're going to go 6 times 8/3 x, and then what's the 8/3 going to be now? 5/3. Took off 3/3. That's right. Yep, always subtract 1 for the power rule, yep. So then what happens here is 6 times 8 is 48. 48 divided by 3 is 16. So this answer is 16 5/3. That is your f prime or y prime.
So the question asks you to differentiate this quantity.
Exactly. Yep. Not too bad, right? This calculus stuff's overrated. Well, there is more applied stuff. There is more applied stuff. But you already know my philosophy on math. Okay, at what points on a hyperbola xy equals 12 is a tangent line parallel to the line 3x plus y equals 0? Yeah, it's a hyperbola. They're doing that on purpose. Yeah, we can divide by x, right? We're not too scared of that. So we can put it in y equals. Okay. And then we want to differentiate that. Okay, and it's going to be a little bit backwards. Okay, because this part, it's giving us, we have to remember what parallel means. So I'm also going to move this over. We want y equals negative 3x. That's the slope we're looking for, right? Negative 3. So we're looking for parallel, so stay with me. Yes, we're going to find the derivative of 12 over x. That's what we're going to do now. Because we still need y prime, because we still got to find the tangent slope, right? So we still want to find y prime, so then what would be an easier way to write y to do this? Good. Okay, so then y prime is what? Good. That's your y prime. Negative 12 over x squared. Okay, so this is where it gets a little bit interesting. So we have the derivative, right? Okay, and we don't have a point, but we have a slope. So how are we going to get this to work into what we want it to be, I guess is the best way to say it. So I want to figure out when the slope is negative 3. So this is what? Negative 12 over x squared. What is that? It is the slope, right? So this is the slope of the tangent line. So we simply set this equal to negative 3. So we're going to go negative 12 over x squared equals negative 3. And now we're going to use some algebra skills to solve. So when you take the derivative, that thing that it gives you is the equation for the tangent slope. and this is telling us they want to be parallel to this tangent slope, the 3x one, which is negative 3x. So we set what we got equal to the negative 3. And that'll tell us where they're the same, where they have the same tangent slope. Yeah, genius. We are geniuses. Okay, so put x squared over here. So negative 12, I threw the x squared over here by multiplying. So I don't have to have this fraction stuff anymore. And then I divide by negative 3. I get 4 equals x squared. So then what do we get? What's that? 2 or? What's that? Nope. Well, yeah, it's root 4. But plus or minus 2. We were thinking 2 squared is 4, negative 2 squared is 4. So you have two options. But I like all the options you gave me. Square root 4. 1 over 4 to the 1/2. Very good. Okay, so that means there's 2 points. That means there's 2 points where this happens. And that's because it's a hyperbola, so hyperbolas have this kind of look to them. Okay, so that means there's 2 points. Now this is why this makes sense. Again, I really like you guys to follow these things all the way through, because we said x plus 2 and minus 2. So that'd be, let's say that's minus 2, that's plus 2, right? The line that they have is negative 3x. So negative 3x is simply just something like this. Do we all agree? So then we're saying our tangent slopes that are parallel to that, that's how that kind of makes sense. Obviously my lines aren't perfect, but that's why there's 2 answers, because that's what a hyperbola looks like. So these 2 lines here are parallel to the one they gave us and going through at 1 point on our graphs. Okay, so now we can figure out those points really quickly. How can we figure out these actual points? Yeah, just substitute the 2 in, exactly. So we can just put the 2 in there. So that would give me, if I put 2 in for x, 2y equals 12, what would I do? Divide by 2, so I would get 6, right? So this is actually pretty accurate, really. So that's 6. Okay, and then if I did negative 2, you'd get negative 6. So 2, 6, negative 2, negative 6. Cool. All right, last one. Everybody looks pretty happy. That's good. All right, a ball is dropped from the upper observation deck of the CN tower. How fast is the ball falling after 3 seconds? This is where we can start using our stuff more applied. Okay, so I didn't put the formula in there, but our function for the ball falling is S equals 4.9 t squared. So we want to figure out how fast the ball is going. So now this is what we need to understand. This is, and I'll wait for you to write this down because it's kind of an important concept that I never got when I was your age because I just kept doing the derivative over and over. Like we're doing derivative with y respect to x. What are we doing derivative of here? S with respect to t. So we're taking the derivative. We're doing s prime, right? What's the question asking? So it's asking for speed at a specific time, correct? So that's why we're doing what we're doing. We're finding the derivative of the speed to figure out so we can be at the tangent of that specific point they're giving us. Okay, because they're giving us 3 seconds. So what they want, in our world of what we're doing, they want s prime of 3. Does that make sense? They want the derivative of the speed with respect to time at 3 seconds. Okay, so how do we find the derivative of this? What's that? Drop the 2 down. We get 9.8 just t, because it's 2 minus 1. And now we simply plug 3 in. That's all you do. And you're going to get 29.4 meters a second is the speed of the ball at 3 seconds. And that's actually real. Like, you can do that. Okay, and that's it for today.